Kimakwa. We have Lydia, Mr. Chara, Patrick, Ron, Safari. Yeah, all those. Tobias, Stanley, karibuni sana. We are glad to have you today for the webinar. My name is Joanne Tanin. Well, I work in the Kenya Space Agency as a Space Education and Awareness Officer. And one thing that we do in KSA is to nurture young talents and inspire those talents and those people that are interested in STEM to ensure that as they try to find their careers, yeah, their path grows well. So just an introduction to the Kenya Space Agency. We are state corporation mandated to coordinate, regulate, and promote all space-related activities in the country. And one of our key strategic area is create national capability in different aspects, growth in space ecosystem in the country. And holding this webinar is part of creating the national capability in the country, that is Kenya. So once again, thank you so much for joining us. We look forward to have an interactive session. So if you have got any question, our chat is open. Just drop your question as the presentation continues. And if you feel your question has not been answered well, we'll have a Q&A session at the end of the presentation. You're welcome to raise your hand. We'll give you a chance to ask the question. Yes, and in between the presentation, you're also welcome to raise a hand for clarification of anything that was not clear to you. Hope that you're going to enjoy. Have fun. So we have our presenter who is called Mr. Stoa. He's an aerospace engineer who's going to take us through introduction to rocket design. So at this moment, let me welcome Stoa.
Okay, good afternoon, everyone. My name is Joven Stoa, and I'm going to take you through the introduction to rocket design. Thank you. So I'm going to share my screen, and so I hope you can all see my screen. So welcome to this Space Club webinar session titled Introduction to Rocket Design, and I'm going to take you through this session. Thank you. So we're going to start with the table of contents. So just give you in a nutshell what we're going to discuss in this webinar. So we're going to discuss what is a rocket, how a rocket works, the rocket trajectory profile, the parts of a rocket, the structural system, and later on we'll do an activity and also do another simulation using SDK and OpenRocket. So yes, welcome. Let us start with so what is a rocket? A rocket basically is a special vehicle designed to be able to travel through the atmosphere past the Kármán line, which is the boundary between space and the atmosphere. So basically, we designed the vehicle to be able to deliver, to have a purpose or a mission, to be able to either do the heavy lifting, either lift a payload or be able to lift. Sorry about that. So basically, a rocket can also be referred to as a launcher or a launch vehicle. So they're designed to be able to carry payload into space. And when we talk about payload, basically we mean the cargo which is delivered to space, or the equipment being carried into space. It can either be humans, if it's for a mission, basically delivering astronauts into ISS, or be able to do orbit maintenance on satellites, or basically injecting satellites into orbit, or injecting scientific instruments, for example, a telescope or a space probe into orbit. And sometimes can be able to deliver food, water, and other scientific experiments on board the International Space Station. So how a rocket works? A rocket works basically on the main four fundamental forces. Basically, we have weight, we have thrust, we have lift, and drag. So the basically weight is just a component of gravity, and thrust is used to be able to overcome gravity to be able to ensure that our vehicle is able to attain the final orbit. While drag is the force that is imposed on the vehicle as a result of the atmospheric, probably atmospheric air. Basically, we're talking about density, factors such as temperature, factors such as wind. Most of those affect the way the vehicle is able to traverse. So basically, there's a way that drag is able to be imposed on the vehicle, and that is why when you are designing your vehicle in terms of your guidance and navigation system, you need to be able to take into consideration those kind of forces, because of course they're going to affect your trajectory. That is why we always have the perfect timing to be able to launch our vehicle, which is called a launch window. So you look at the atmospheric conditions, how are the winds, how is the atmosphere, how is the density, how is the weather. All those factors, you factor them before you're able to launch your vehicle, because all these forces are going to affect the way your propulsion system is going to work, and if you are going to be able to achieve your final orbit. And then in the next slide, you're going to see how these forces are being factored into the design of the rocket engine. So the rocket trajectory profile. Of course, we always understand that when a rocket is launched from the ground, it never really goes straight up into the atmosphere. It reaches a point where it's able to turn. And that turn is what we call the gravity turn maneuver. They tilt during flight. So I want you to imagine this. You're flying to space. Think of a rocket like a super powerful aircraft, which is flying straight up. Of course, it will eventually run out of fuel and fall back to Earth. Be able to stay in space, this vehicle needs to be able to go very fast, because the satellite needs to attain the final orbit. And it's going to be orbiting at a velocity of around 28,000 miles per hour. That is around 7.6, 7.7 kilometers per second. So to be able to do that, we need to ensure that our vehicle is going to perform a gravity turn maneuver and be able to attain the final orbit. So another thing I want you to be able to imagine is gravity and speed. As the rocket is going very high, it needs to be able to tilt, because you're going to have to, let me put it this way. There are losses, of course, because nothing operates as a 100% efficiency. There are losses. And these losses need to be able to be factored during the design of the rocket engine. And these losses, there are 4 types of losses. We have the drag loss, which is because of a result of the atmospheric density, as a result of the atmosphere properties. Then we have another losses, which is called the gravity loss. So basically, gravity loss is that as you're trying to overcome gravity, you're going to lose thrust. That is part of your velocity, delta V velocity, that is used to be able to accelerate the vehicle. So the reason the vehicle needs to be able to tilt is that as you are rising, your thrust is being used to overcome gravity. But then it will reach a point that if you go straight up, you run out of fuel. So to avoid running out of fuel, the vehicle needs to be able to tilt so that gravity is acting perpendicularly to the vehicle in such a way that thrust from the rocket engine is used to push the vehicle straight into orbit rather than being used to overcome gravity, because then it's going to be counterproductive. So that's the reason the vehicle needs to be able to turn and perform the gravity turn maneuver. And also the other reason is because as you're going high up into the atmosphere, your density is decreasing exponentially. So as your density is decreasing exponentially, your vehicle is going to undergo drag loss. And that is why sometimes we always ensure that our vehicle is able to accelerate very, very fast during the initial stages of launch, so that you can be able to escape the thick parts of the atmosphere. While it's escaping, then that is when it starts performing the gravity turn maneuver. So basically, you're doing the gravity turn maneuver to be able to minimize drag losses experienced with the vehicle, and you're also trying to minimize your gravity loss. The other loss is called the thrust vector control or the steering angle, steering losses. We call it steering losses. The same with an aircraft. When an aircraft is taking off from the runway, there's that angle, we call it the angle of attack. So basically, AOA. We need to ensure that if our aircraft is taking off from the runway, if the angle is more than 16 degrees, the aircraft is going to stall. So for a rocket also, we always tend to ensure that the steering angles are very small, so that we do not subject the vehicle to too much aerodynamic stresses as the vehicle is ascending into the atmosphere. So the reason it turns is also to be able to minimize steering angle losses, so that you do not have too much drag or aerodynamic stress being subjected at the tip of the vehicle. So that is the reason you need to be able to turn, perform the gravity turn maneuver, and then be able to attain the final trajectory into orbit. And the other one, the other losses basically is for the pressure difference in the atmosphere. That comes in particular when you're designing an engine, to be able to factor in the aspects of over expansion, under expansion, and ideal expansion for the engine, because you need to be able to ensure that the pressures are balancing the pressure from the exhaust and the pressure within the atmosphere. So you need to ensure that you design your vehicle in such a way that the engine is able to balance because the higher you go, there's a difference in pressure. So you need to be able to account all those factors when you're designing your engine. So why we tilt? Because we want to be able to have less fuel wasted. The way I told you, you don't want to use your fuel to overcome gravity. Rather, you want to use your fuel to be able to accelerate the vehicle and push it into orbit. Yeah. Then the other thing is you want to be able to go very, very fast. So that is the reason you also tilt. Then you want a smooth ride. So flying sideways helps the rocket avoid too much air resistance, which I call drag loss, and to make the ride smoother and safer. And that's why when you hear these rocket launches, you always hear when they say the vehicle is max Q, the vehicle has passed max Q, and the rocket engineers are very happy. Max Q basically is maximum dynamic pressure, and maximum dynamic pressure is a function of air density. So that is when the vehicle has undergone too much stress. So we are very happy that the vehicle has already passed the point where it's being subjected to too much aerodynamic stress, and that is why we always say the vehicle is max Q. Then parts of a rocket. So basically, a rocket is composed of several systems, which because it's a system of systems approach. So you have the payload system, which basically consists of any spacecraft, astronauts, cargo, or probably spacecraft modules which are going to be integrated on board the ISS. Then we have another part called the structural system. The structural system consists of all other components that are remaining, from the body tube to the nose cone, the fins, basically everything comprises of structure. The struts, everything that forms. I can give you a simple analogy. So basically, like a human, you have the bones, you have the skin. So everything that forms the structure is basically the structural system. Then you have the guidance system. The guidance system is basically like the brain of the rocket. It's able to guide the rocket. You have the radars, you have the computers, you have the antennas, everything. So for example, when you're launching our vehicle, we need to be able to receive telemetry that this is the way the engines are the propellants in the engine are being spent. This is the way the vehicle is approaching. This is the altitude the vehicle has reached. So all those are performed by the guidance system, which is basically the brain of the rocket. Then, of course, we have the propulsion system, which is basically the engine that drives the rocket in to be able to attain those higher speeds. And you can be able to see on your right, we have the SLS, which is the Space Launch System that's going to be able to do the Artemis mission. So you can be able to see how from this simple schematic to this very complex schematic. You can be able to see the space launch system, which is going to use the RS-25 rocket engines that are used in the space shuttle. Then they are also going to have the solid rocket boosters, the core stage. All of these are just structures. They form the structural part of the rocket. But then you go deeper, then you will find that, for example, the solid rocket booster is basically a propulsion system. Inside you have the propellants, with the solid propellant and the igniters. All those form part of the propulsion system, but they are basically the structural system. So when you look at this, you're seeing a schematic which forms the basic structural design of a rocket. This one is going to be able to take astronauts to the moon in the Artemis mission. Then there's a reason we stage rockets. Why do we stage rockets? Sometimes you see those heavy rockets with several stages, such that when one stage is completed, it's now dropped. So the vehicle is cutting away as it's going to orbit. So rockets are built in particle stages to be able to help them to get more easily into space. So imagine this: you're building a tower with blocks. Think of building a tower with blocks. If you have to carry all the blocks at once, it will be very heavy. But if you carry a few blocks at a time, it's much easier. So rockets operate in that similar fashion. So how are rocket stages work? So the rocket stages are just different parts, which consist of an engine, the fuel, and a flight computer. Tracy, I see your hand is up. Hello, Tracy. Okay, fine. So the reason we stage a rocket is that we want to be able to ensure, imagine you have a high performance car, for example, a Ferrari. You want to be able to get from 0 to 400 miles in probably 0 to, I don't know, 10 seconds, 5 seconds, the way you want it. And then once you accelerate, then the brakes fail and you're trying to stop the vehicle. You can imagine what is going to happen. So the reason we stage the rocket is that we want to be able to ensure that we are able to control this vehicle at different stages of flight, so that we have the main engine cutoff, the secondary engine cutoff, those kind of stuff, those stages, so that we can be able to keep our vehicle within a controllable speed. Then the other reason is that we want to be able to increase efficiency, such that we use the initial momentum from the other stages to be able to keep our vehicle going very, very fast. Because as you shed weight, which we call dead weight, then your vehicle keeps going on fast and fast, so that you can be able to attain the final orbital velocity, which is 28,000 miles per hour, to be able to inject a satellite into orbit. So the reason we drop off the parts, we call it jettison. You jettison the spent stages, you jettison them. So in such a way that you can be able to ensure that as the first stage has already completed its fuel, we no longer need it, so we drop it off. And we make the rocket more lighter so that it can be able to travel very fast. The other thing we do is, as the stage is separating, we are even going faster until you're able to attain the final orbit. Why does this staging help? Staging helps in terms of weight. You lessen your weight by dropping off the dead weight. So you cut off the extra stage that has already been spent, you drop it until you remain with the upper stage, which basically consists of the payload. Then the better speed. Each stage helps the rocket to be able to speed up more and more until it's going super fast, over 8 kilometers per second. That is what I told you. We want to ensure that our final velocity to inject the satellite into orbit is going to be more around 28,000 miles per hour, which translates to about 7.6, 7.7 kilometers per second. Then, of course, like a relay race, imagine a relay race where runners pass the baton. Each runner does their part and then lets the next runner take over. You can see this in Usain Bolt and the marathon stuff. So rocket stages are like those runners, helping the rocket to go higher and faster until it reaches space. So on your right, you can be able to see the multi-stage rocket infographics element. We have the 3-stage launch vehicle and 2-stage launch vehicle. So you can see we have the first stage launch vehicle, which basically consists of this one is a modular staging. So stage in terms of boosters, you have to see the boosters are arranged in a modular way, that is in a circular way around the main rocket. Then you have the second stage and the third stage. So for example, the Saturn V, which is the most powerful rocket ever built by humans was a 3-stage engine. Then, of course, you have the head of a fairing engine. Then you have a 2-stage launch vehicle. For example, the Falcon Heavy for SpaceX. It's a 2-stage launch vehicle. Then there's a rule of thumb in rocket design. You cannot have more than 3 stages, because if you increase your vehicle to have more than 3 stages, for example, 4-stage rocket, you're increasing the number of failure points. And also the efficiency for each additional stage tends to be able to decrease. So basically, you're going to have to lift more mass while making your vehicle to be less efficient. Basically, what I'm saying, you're increasing risk. When you increase risk, basically risks, you need to be able to ensure that when you're designing your vehicle or your launcher, you keep your risk to the minimal. Because when you are increasing the number of stages, you're also taking into account the cost of design. You're raising the cost of design. So in engineering, you work within budget. So you need to be able to keep your risks very low. You need to be able to also contain your vehicle. For example, if you do a 4-stage launch vehicle, and then the second stage fails to separate, you're going to lose your vehicle. Yeah. Jahesh, I can see your hand is up. Hello, Jahesh. I can see your hand is up.
Hello.
So we'll continue. Yes.
Sorry, I have a question.
Yes.
What is the name of the force that a rocket produces to accelerate a spacecraft?
What is the name of the force?
Force that a rocket produces to accelerate a spacecraft.
You're saying a force?
Yeah, that a rocket produces to accelerate a spacecraft.
Yeah, we call. Basically, it's called thrust force, which is the summation. Okay, it's called a thrust force, and this thrust force is as a result of having the pressure. You know, we have two components. Okay, Tracy, we have two components that contribute to the thrust force. So basically, one of the components is called the pressure thrust. That is the thrust resulting from the pressure difference between the engine and the atmospheric and the atmosphere. So we call it the pressure difference between the engine, because the engine, the propellants or the combustion products are coming out at very high pressures. So that pressure at the exit of the nozzle and the difference between the pressure in the atmosphere is what contributes to what we call the pressure thrust. Then we have momentum thrust, which is basically mass times the velocity. So velocity at the exit times the mass flow rate. That contributes to what we call the momentum thrust. So the thrust force from the rocket is the combination of these two. When you add the pressure thrust and the momentum thrust, you get your thrust force, which is used to accelerate the vehicle into orbit. But during design of the rocket, we always ensure that the pressure difference, that is the pressure, when you take the pressure difference from the engine and that of the atmosphere, that value must be 0. If the value is 0, then it means that the only contributing factor to thrust force is basically momentum force, momentum thrust, which is a byproduct of the mass flow rate in the engine and the velocity at the exit. So that is what contributes to momentum thrust. So pressure thrust never really contributes to the thrust force of the rocket, because we always design our rockets to ensure that the pressure difference is balancing. That is the pressure at the exit and the pressure at the, of the atmosphere, that is the surrounding atmosphere, is balancing. And that's why that's also another reason why we stage rockets. We stage rockets to ensure that we're able to account for the pressure difference, because a rocket engine designed for sea level cannot be able to operate in the vacuum. There's a difference. Even when you check in the terms of design, the length, the operation, they're different, because we always account for, we design the rocket engine to be operate at different altitudes. For example, a rocket engine designed for sea level cannot be used to operate in a vacuum level. So that is why we always ensure that we stage rockets so that the engine that is used for sea level, once it has done its work, it's jettison, then the other engine that is used to be able to inject the orbit into the vacuum of space, then can be able to take over and push the satellite into the final orbit. Yeah. So I hope I've answered your question. The force is called thrust force, and it's a result of momentum thrust and pressure thrust. But as I've said, when we design our engine, we need to ensure that the pressure of the atmosphere and the pressure from the engine exit, they're balanced. So when you do the difference, it gives you a zero. I'll show you the formula in the next slide.
Okay, thank you.
Thank you. Okay, so the structural parts, we're going to the structural parts. So a rocket has very many important parts that help it to work. So we're going to learn about them. One of them is called the body tube, which basically forms the whole shell of the vehicle. And it's the main part of the rocket, which holds everything together, keeping the rocket strong. Basically, we can say it's the chassis for the rocket. The same way we have the vehicle, we have a motor vehicle, basically an automotive, a car. It has the chassis. So you see the chassis, which basically is the shell or the skeleton of the vehicle. So the body tube also forms part of the exoskeleton of the vehicle. The same way you have bones, you have skin. So it's the same way you have body tube, which has the struts, the skin. So the grid fins, special fins that look like tiny grid fins, they help guide the rocket when it comes back down on Earth, so it can be able to land safely. We also have a nose cone, which is always the pointed top of the rocket, which helps the rocket to be able to go smoothly through the air. I'll show you that. Then we have the payload fairings. The payload, as we remember, the payload in terms of definition for a rocket is basically what is being carried on the upper stage vehicle. Sometimes payload can also be used in terms of satellite. When you have a satellite in orbit, the payload is what dictates the mission of the satellite. For example, if I launch an Earth observation satellite, the payload is going to be an imager. So basically, that is the payload, basically, which dictates the mission of the satellite. But for a rocket, a payload is basically what is being carried or delivered into space. As I said, it can either be a human astronaut, that is for manned mission. For unmanned mission, basically it can be satellites, it can be scientific instruments, it can be cargo. Then you have the skin, which is the outer layer of the rocket. Like its skin, it protects the inside parts of the rocket from heat and pressure during the flight, which I'm also going to explain. And also the payload fairings, those coverings, they're just coverings. They're used to protect the spacecraft payload, or for example, humans against the impact of dynamic pressure, as I said, max Q, and also aerodynamic heating during launch as we go through the atmosphere. Then I'm going to explain the structural parts. As you can see, we have the body tube, we have the nose cone, we have the fins, and the launch lag. So this one is just a basic model of a rocket, for probably a sounding rocket. Yeah, this is just a basic model. Then, of course, the body tube, the basic building block of all rockets. All rockets have the body tube. For example, you have an upper body tube, lower body tube, the motor. This comes in when you're designing a sounding rocket. Then the motor mounts, engine blocks, launch lag. I'll explain all this in the simulation for the Open Rocket software. So fins, as we said about fins, the same way with fish. Fish have fins to be able to steer them through the water. They act as a form of a guidance system. So rockets need to fly straight and go into the right direction, and fins help them to do this. So let us see how these fins work. Imagine this: you have an arrow. You are launching an arrow from a bow. So think of an arrow with feathers at the back. The feathers help the arrow to fly straight. Rocket fins work in the same way. So how this rocket fin works? For small rockets, for example, a missile like this one. This one is a missile. Or a sounding rocket, the fins help to be able to keep the rocket stable and going in the right direction as it flies. Because when a rocket experiences a wind gust, for example, wind from a different direction, it tends to be able to deviate its trajectory. But because we have fins and they are arranged in a uniform way around the body tube, they're able to ensure that the vehicle is able to maintain its stability within the roll axis. Yeah. Then for bigger rockets, for example, the Falcon Heavy, the Starship booster, they use a special types of fins called the grid fins. I think you've seen this in the Falcon Heavy boosters when they come to land, and also in the Starship booster, the one that SpaceX is going to use for interplanetary missions. They use these grid fins to be able to stabilize the booster when it's coming to do the flip maneuver to be able to land. So they use the grid fins to be able to stabilize and make sure that the vehicle is able to reorient itself along the roll axis. So why are these fins very important? These fins are very important to be able to keep the rocket stable so that it does not wobble or spin out of control. For example, when there's a wind gust, that kind of stuff. And also they're used for control landing. If we go back, you can be able to see this. This is I will explain the profile. We have launch, powered ascent, then the main engine cutoff. That is what we call the MECO. Then with ballistic reentry, it can either be recovered from the ocean. For example, for the space shuttle mission, they used to be able to recover the SRBs, the solid rocket boosters, by dropping them into the ocean because they are the most expensive part of the space shuttle mission because you need to be able to reuse them, the boosters again. Then SpaceX came into the picture and then they started doing controlled reentry. So they're able to land their booster. And with this, you need fins. You need to have thrust vector control. So basically, when you launch your vehicle, you need to be able to ensure that there's a minimum threshold of propellant that is left to be able to perform this first reentry burn attitude control, then second reentry burn, and then from there you use your fins, those grid fins, to be able to stabilize and ensure that the vehicle, the booster, is able to deploy the landing legs and is able to land on a pad along the ocean, on the ocean. This is what happens. You're able to see. Then you can see these are the grid fins which have been deployed, and they're always in a stored position during launch. Yeah, these ones. For the missile or sounding rockets, they're used for stabilization. They also form parts. They can either be a wing or a canard, which are used to stabilize the missile during its mission. Then, as I said, we have the nose cone and the payload fairing. So the nose cone is the topmost part of the rocket. So, for example, for the sounding rocket, we always have the nose cone, and you can be able to design your nose cone based on whatever mission you are doing. So rockets have special parts that help them fly smoothly and protect what is inside, basically the nose cone and the payload. So what is a nose cone? It's the pointy top part of the rocket. And what does it do? So it's the first part of the rocket that interacts with the atmosphere. So it's used to be able to protect the vehicle and shield the payload or whatever is being delivered into space. So that's what it does. And the different shapes for the nose cone depending on your mission. It can either be rounded, can either be pointy like a pencil, for example, this conic one. But mostly when we are designing rockets, we tend to either go with the elliptical, tangent, ogive, and parabolic. This one is a bit dangerous. We shall see the reason. Then, of course, the payload fairing is a special cover that goes over what is carrying the rocket like a satellite. This one is called the payload fairings. And these fairings are always jettisoned when the vehicle has attained probably around 200 and 250 or 200 kilometers from the ground when it's close to space. So you need to be able to jettison and expose the payload to the space environment as you prepare to inject the satellite into orbit. Then I can go back and show you here. You have launch, then you have powered ascent, main engine cutoff. This is basically serial staging. So you have the second stage burn, then the orbital altitude. So this one is just a plot of altitude against downrange. So basically you have altitude, which is the orbital altitude, and then you have orbital velocity. You can see payload separation. And the payload separation is basically where you're going to separate your fairings. Now you have exposed your vehicle. So your vehicle, when I said the vehicle, basically I'm talking about the payload. So the spacecraft that is being injected into orbit. So here is where you're going to have to jettison the fairings because you no longer need them. Here, yeah. Then what does it do? The payload fairing basically protects the satellite from strong winds and heat when the rocket is launching. Once the rocket is high enough, the fairings opens up and lets the satellite out. That is what is happening here. Then I want you to imagine this. You have a nose cone, which is basically a car that is going really fast. The front of the car is smooth so that it can be able to move through the air easily. Basically, we talk about aerodynamics. So you can see the way Ferrari, Lamborghini, they're very, they have very low center of gravity and their shape is very different from these big SUV cars because they need to be able to go very fast. So the shape needs to be able to be very aerodynamic. So that's the reason also cones are designed to be that way. And the reason we go with this and elliptical rather than conic, you will see for different missions. For example, a missile is different from a rocket. So a payload fairing, imagine wrapping a fragile toy. You know, you have a toy in a bubble wrap to be able to keep it safe. So the payload fairing is like a bubble wrap protecting the satellite until it gets into space. Yes. So this is the question I wanted to pose. Why do space capsules and rockets have rounded and blunt nose, while missiles have pointed nose? Well, we shall see. Different kinds of flying things have different shapes for their noses. Let's find out why. So for space capsules and rockets, basically a space capsule is this one that carries astronauts from space back to Earth. So it's doing a deorbit band. Then from there, it's going to reorient itself in such a way that this front part, which is blunt, is the one that is exposed to the atmosphere. And remember, this vehicle is deorbiting from space. So it's going to be re-entering the atmosphere at around 28,000 miles per hour. You can imagine that is around more than Mach 25. So basically, this is a hypersonic mission. So basically, re-entering the atmosphere at those very high speeds. So the reason that we ensure that the space capsule is blunt is able to ensure that we deflect as much heat away from the vehicle as possible, while keeping the astronauts in the capsule safe. That's the reason this front part is always shielded. We put something called TPS, thermal protection system. Basically, it consists of ceramics and ablative materials which are able to wear when they're exposed to the atmosphere aerodynamic heating. And the other thing about aerospace that is very interesting is that engineers decided to see that, for example, if you're designing a vehicle that is blunt, cutting through the atmosphere is going to go very slow. So the reason we designed them to be blunt is that during re-entry, to be able to decelerate the velocity of this vehicle, we need to be able to keep it blunt so that as it's experiencing the aerodynamic drag, we're also using that drag to be able to slow our vehicle while also guiding the vehicle. So we are using that drag to slow the vehicle and also guide the vehicle to ensure that we're able to keep the astronauts very safe. So I will explain again. When rockets and space capsules come back to Earth, they go very fast and get very hot. The rounded shape helps spread out the heat so they don't burn up. It also helps slow them down safely when they re-enter the Earth's atmosphere. The technical term for slowing down, we call it aerobraking. So basically, you have seen a Bugatti Chiron, that high supercar, the one that can go more than 400 kilometers. I'm not sure. Yeah, 400. So basically, 400, you have to put something at the rear of the vehicle. We call it a boot spoiler. You can see at the rear of the Bugatti, there's a tail that always pops up. It's like a tail. We call it a boot spoiler. So it's used to spoil the flow to be able to reduce the speed of this car very, very fast. So that, in a technical term, is called aerobraking. You use aero, that is aero, like an aeroplane. Then from the, you remove the plane, you put braking. So you use that as a brake to be able to slow yourself and re-enter the atmosphere very slowly, so that the parachutes can be able to deploy and also help you to be able to decelerate your horizontal velocity. So that's the reason we use a blunt shape. And also for rockets, you can be able to see from these NASA launch services too, the launchers are blunt. Let's go to the missile. The missiles are usually pointed because they need to be able to move quickly and smoothly through the air to reach their target. And that pointy shape helps them to cut through the air more easily and fly faster. That's why you can be able to see from the India tactical ballistic missiles and the ballistic missile defense interceptors that they have very pointed noses so that they can be able to cut through the atmosphere very, very fast. And when you research on the profile, like the trajectory profile for a missile and that for a rocket, they're completely different. For a missile, the trajectory is going to have a ballistic, that is, it's going to come from from ignition, that is the boost phase, to coast phase, and then from there we have the terminal phase. So it's going to have something like a curve, a U. But for a rocket, the trajectory profile is completely different. So the reason is that they need to be able to cut through the air more easily and fly faster. So imagine this. You have a rounded nose. Think of a car with a big round front bumper. It can push through the wind gently and stay safe. Rockets and space capsules have rounded noses to handle the heat and stay safe when they come back to Earth. And a fun fact about this aerodynamic heating is that this surface always glows at 6,000 degrees Celsius. Like it's the surface of the sun, because this thing is encountering the thick parts of the atmosphere, so it's going to generate a lot of heat. And something always happens that during this aerodynamic heating, this space capsule always loses communication with the mission control. It's something called blackout. So we have blackout communication because you cannot be able to transmit signals through the hot plasma, the one that forms at the front of this vehicle. So there's no communication, and the vehicle is on its own. Basically, it's using INS, that is inertial navigation system, to be able to guide itself, gyros, accelerometers, to be able to guide itself until it's able to do the splashdown into the ocean. So the pointed noses, think of a fast airplane with a sharp nose. For example, the Concorde, F-35, F-15, the military fighter jets. You can be able to see they have pointed noses because for them, they do supersonic missions. So they help them to go very fast. So missiles have pointed noses to move quickly and reach their targets fast. That is the reason why these things are designed that way. Yeah. Then we're now going to the rocket engine parts. So the liquid rocket engine, from the name liquid, basically from the name liquid is that everything is liquid, from the fuel to the oxidizer. And when you take a fuel and you combine with the oxidizer, you have something called a propellant. So basically, we say liquid propellant. You're combining a fuel and an oxidizer to get the propellant. So basically, this is the fuel and the oxidizer. Oxidizer is basically oxygen. It can be something different, but it's basically oxygen. And fuel is basically, it can either be liquid hydrogen, it can either be methanol. For example, the SpaceX Raptor engines, they use methanol as fuel and then oxidizer as oxygen, LOX. So it's called Methalox. But here we use, for depending on your selection, as long as everything is liquid, then it becomes a liquid rocket engine. So a liquid rocket engine uses special liquid fuel to help it fly, and also oxidizer. So let us learn parts of the liquid rocket engine. So as long as you have liquids, you'll need pumps, because even in your households, you have pumps to be able to pump water at very high pressure, because otherwise using water at very low pressure is useless. So that is the reason that you also need to be able to have our propellant, basically the combination of fuel and oxidizer, to be pumped at very high pressures into the combustion chamber. So the pumps, they help move the fuel and the oxidizer quickly and with high pressure to where it needs to go. Then we have the turbines. So when you combine turbines and pumps, you get something called a turbo pump. Yeah, that is the definition. I call it turbo pump assembly. You have combined your turbines and the pumps. So the turbines are used to be able to drive the pumps to ensure that they spin really, really fast to be able to push the propellants through the combustion chamber. So that's the reason we have turbines. For the tanks, you also need to store your fuel. And this fuel, remember, and the oxidizer, they're stored at very low temperatures because they're cryogenic propellants. So you store them at very low temperatures. That's why you need very special tanks. And these liquids are kept very cold. So they're called cryogenic propellants. For example, if you have watched these sci-fi movies, they want to preserve people at very low temperatures to ensure that they're able to, survive the, interstellar travel or, deep space missions. So there's cool people at very low temperatures, cryogenics. Then, of course, we have the fuel lines. Fuel lines just like straws that carry the fuel from tanks to the pumps. Then we have the combustion chamber, where the fuel and the oxidizer mix and burn, and then they eject a lot of pressure. Then, of course, we have the nozzle. The nozzle is the most, I would say complex part, because there are very specific angles that you need to take into account during the design of your nozzle. We have the converging section, you can see here, the converging section. Then we have the diverging section. So that those angles, we call them half angles. You can have a convergence half angle, you can have a divergence half angle, 15 degrees, 30 degrees, depending on your design. So the nozzle is like a funnel. Basically, it's a bell-shaped engine. So bell-shaped, it looks like a bell. It's used to accelerate the hot gases from the combustion chamber and shoot them out very fast, push the rocket forward, basically the thrust force. Then, of course, we have heat exchangers, which are able to manage the temperature inside the rocket while keeping things too hot or too cold, depending on what you want. Then of course you have valves. You need to be able to open and close. The interesting thing about liquid rocket engine is that you can be able to either shut them off and then reignite them off. So there is something, we call it throttling an engine. When you throttle an engine, is basically you're able to start and then shut it down immediately. That is the difference between a liquid rocket engine and a solid rocket engine. A solid, everything is solid. You cannot be able, once you have lit up a solid rocket engine, you cannot be able to stop it until it has already completed everything inside the, the body tube or the, the solid rocket booster. You need to be able to complete everything, and that's the reason why solid rocket boosters are used for the heavy lifting, so that you can be able to lift the core stage very, very fast through the thick parts of the atmosphere. Once the work is done, you drop them off. That's the reason we use solid rocket boosters for those heavy missions such as Ariane launch vehicles, the space launch system for the for NASA, SLS, and then we also use it for Saturn V. We used the solid rocket boosters. Even the space shuttle mission, we used the solid rocket boosters to be able to do the heavy lifting. Once the heavy lifting is done, you drop them off. So you can see the basics of rocket science. As I was saying, we have the PO, which is basically the exhaust pressure, and then you have the pressure exit. So when you design your engine, you need to be able to take into account, you need to be able to ensure that you balance this pressure exit and the pressure atmosphere, which contributes to pressure thrust of the engine. Then you combine this mass flow rate and velocity at the exhaust, you get what you call the momentum thrust. So most of the time we always ensure that this and this balance so that they cancel out, because when you take the difference of this and this, it becomes zero. So basically this and this don't really contribute much to the propellant. This is the schematic. But then a complex schematic is this one. You have the oxidizer, you have the fuel, you have the fuel boost pump, you have the turbines, which are used to drive the pumps. Then you have the oxygen boost pump. Then you take them through the combustion chamber, the nozzle. Sometimes you can be able to take this fuel, you can be able to see the fuel line, the way fuel is flowing. So the fuel sometimes can be taken around the combustion chamber to be able to cool the nozzle. When it's cooling the nozzle, it's then fed back into the combustion chamber so that it has high specific heat capacity. So imagine you're taking something from low temperature and then you're passing it through something very warm. It means that you're increasing the energy of that fuel so that when it's going through the combustion chamber, it's going to burn very, very fast. That's the reason sometimes they pass fuel around the nozzle. It's called regenerative cooling. You cool you pass the fuel through the nozzle, through some pipings, so that you can be able to increase its temperature so that when it's going through the combustion chamber, it's able to burn very fast. Then, of course, we have something called a hybrid rocket engine. From the name hybrid, it's basically a mix of solid and fuel. So let us see how a hybrid fuel chemical propulsion system works. So from the name hybrid, it basically means mix of two things. And in hybrid rockets, we mix a solid fuel and a liquid fuel. So this is the most safest type of rocket engine, because you have your liquid oxidizer and you have your solid fuel, and then you have a control valve. So this one, you can be able to control it. You can either control the valve. When you ignite, you can be able to control the way the burn rate is going to happen through this engine as compared to a solid rocket engine. And of course, the fuel is always solid and the oxidizer is always liquid and is stored in tanks. And the application for a hybrid fuel chemical propulsion system, the company called Virgin Galactic, which is basically planning to do space tourism. And of course, in 2021, about there, they launched astronauts just before they come online. So yeah, the Starship, their spaceship vehicle basically uses a hybrid form of chemical propulsion system. Okay, so I think I've come to the end of my presentation. The next thing we're going to do is an activity so that you can be able to see what really goes into the aspect of design. A very simple activity, and then I can be able to show you a simple design of a rocket in two types of softwares. So for the activity, welcome to the exciting world of rocket engineering. You are now the lead rocket engineer for Tembo Industries. So basically, Tembo is just a name, a space exploration company in Kenya, and your mission is to design, develop, and launch a rocket carrying a special Kenyan satellite called Mwewe. Of course, Mwewe is just an eagle in Swahili, which means eagle, not in Swahili, but in English. Yeah. Then we have Kenya Space Agency has given you a budget. It can either be any other company, gives you a budget. As an engineer, maybe you have been given 20 million Kenyan shillings to be able to make this dream come true. So we're going to get started. So you're going to gather your team, brainstorm ideas, create your rocket design. And remember, the goal is to successfully launch the Mwewe satellite into space while staying within your budget and keeping the risks very low. Good luck, young engineers. So for this rocket activity, there are things we're going to have to revisit. For example, we discussed about rocket stages. So we're going to optimize. Do you want to use a single stage to orbit launcher? Do you want to use a two-stage? Do you want to use a three-stage? Of course, using a two-stage, it becomes more complex, but can go much higher and further. Using a three-stage, the vehicle becomes more powerful, complex, but it's more expensive. So we're going to do something called trade-off. For example, if I ask you that, should I give you probably 1 million right now, or I give you 100,000 shillings for the next 12 months, which one will you take? Of course, somebody who is smart will say, I want to take 100,000 shillings for the next 12 months so that you have 1.2 million shillings as compared to someone who takes 1 million right now. So it's about trade-off. What do you really want and what really fits into your design and the budget? Then, of course, you're going to choose your propellant type. Do you want a solid engine? Do you want a liquid engine? Do you want a hybrid? Of course, also your shape, you're going to also choose your shape. The control mechanism, you're also going to have to choose your control mechanism and ensure that you work within the budget. So allow me to stop sharing this so that I can be able to share the activity. Thank you. Okay. So welcome to this activity. So basically, it's a rocket lab, and the site is called How Things Fly Education. So briefly, your mission is going to be a suborbital flight, and as I said, you need to be able to take into consideration so we're going to start to design our vehicle. So the first thing that we're going to do, we're going to optimize the shape. So for our first design, we're going to choose the shape. So you can either have a tapered. So we'll go with tapered. And of course, look at the budget. I want you to be able to look. We have select components to launch. You have your shape, you have your propellant. It can either be a solid fuel, a liquid kerosene, a liquid hydrogen. You have your control mechanism. You either have movable fins, you either have thrust vents, you either have gimbal engines that are able to change their orientation. You can either have a one stage, a two stage, and a three stage. So let us begin. And I want you to be able to look at the budget here and look at the cost and the aerodynamics, the way things are varying. So for our first simulation, we're going to take a cylindrical shape, and we're going to take a liquid kerosene. I want you to be able to see the way cost, the risk, and the thrust are varying. Then, of course, for the control, we're going to use thrust vents. You can see the way the budget is now changing. If you use gimbal engines, you're going over budget. If you use thrust vents, that's still within the budget. Then the number of stages, we're going to select 2 stages. You can see that we are within the budget, but everything is completed. You no longer have any cash. So in case there's any failure, you cannot be able to do anything. You can be able to see the cost, the risks, and also the lift of weight. So we can proceed to launch. So now this is the pre-flight check. The engineers are conducting a pre-flight check. So you're ensuring that everything is going to work properly. And as we said in rocket launches, we always say you are either go for launch or no go for launch. No go for launch, it means that you have detected there's an anomaly or there's a defect, or one of the systems within the rocket is not performing as expected. So for example, and the rule is you cannot be able to launch a rocket when there's a warning in your pre-flight checks. For example, here we see that we have a warning, the rocket check failed because of the propellant issue. They're using liquid kerosene. So if we decide that we are going to launch this rocket, you're going to see what going to happen, because eventually you're going to lose this vehicle. So let us proceed with launching the vehicle. You can see the propellant system malfunction, the rocket has exploded, and therefore you have a mission failure. So now what do? As you know, engineering design basically consists of something called iteration. So you need to go back to the lab, to the drawing board, try to do something we call, what do we call it? Troubleshooting, to be able to identify the root cause. So in rocketry or in space aerospace systems, we call it RCAT, root cause analysis. So we go back to the root cause analysis and be able to see what was the root cause of this failure. So we go back to the lab. Of course, we know that there was a problem with the propellant system. So when you go back to the lab, we're going to identify what caused the rocket. Was it probably a malfunction in the pumps or the turbine assembly, or was it the problem with the liquid propulsion system? So we go back to the lab. This time, we're going to adjust. Now we're going to try another one. I'll show you why these things don't really work. So for the shape, we're going to use a tapered shape. Then we use the propellant liquid kerosene. We're still we're still not within the budget. We have over budget, and you can see the risks. Then we're going to control. We're going to use movable fins. You can be able to see where we're okay, but the budget is already depleted. And then we're going to remain within 2 stage, because if you add 3 stage, you can see your cost is increasing. So you cannot be able to launch this mission because we're not working within the budget. So we decrease. And you can see when you decrease the stages, your cost is also decreasing. You increase, the cost is increasing down here. So we'll go with 2 stage, and then we're going to launch it. Pre-flight checks, you're conducting that everything is going on well. You see, the rocket check failed because of a stage separation issue. And if you decide, if you're the mission, you are the flight, what will I say? You're the flight director for this mission, and you decide that you're going to continue with this launch, then mission failure is inevitable. So let us go and launch the launch. All systems terminal, rocket is supersonic, maximum Q, full throttle up, we're okay. Then no problem. Stage 2 separation malfunction. You have lost your vehicle because there's a problem with the stage separation. So the rocket is exploded and you have lost the mission. So we go back to the lab again. That is always, and that's why you need to be able to be very patient. So before you launch a rocket, you do simulations, virtual simulations. That's the reason they do virtual tests before you're able to do an actual test. And also they do tests for every system before you assemble the final rocket together. So let us try another one. I hope this one is going to work. So flared, then we're going to solid fuel, then we're going to thrust vents, then we're going to a 2 stage, which is okay. You can see the cost is okay, the risks are very minimal. If you increase 3 stage, you can see the risk has gone very high. That's the problem with using more than 2 stages. And that is why currently I don't think there's any 3-stage launcher that exists. Falcon Heavy is a 2-stage. What else? Ariane is a 2-stage. So we can go back. We can reduce our risks. And you can see if you increase a 3-stage, it means your lift of weight from the ground increases, so you can be able to lift more payload. But lifting more payload at the expense of risk, it doesn't really, it's counterproductive, because eventually the mission is going to fail and you're going to lose your payload, probably whether it's a satellite. For example, James Webb Telescope, if you have a $10 billion investment with 10 years, and then you're going to launch it in a vehicle that has risks which are more than the lift of weights, then you're going to lose the mission. So we're going to reduce it to a 2-stage. Then we're going to launch it. So pre-flight checks, propellant is a go, testing control, warning, control issue. Continue to launch. see, the problem with the control system, so the vehicle will never really attain the final trajectory. Okay, back to the lab. Now let us just do a very simple vehicle that can be able to probably work. So let us go with a tapered propellant, probably liquid kerosene, control, movable fins, stages, a two-stage. This one is okay. Let us see. Please work. Please work. I hope we work. This one is going to work. Okay. Now let us see a successful mission. Are we go? Then you ask the mission. We call it the Ranger Safety Officer. Are we go for launch or no go for launch? We are go for launch. So continue launch. All systems nominal. The rocket is supersonic. Max Q. Full throttle up. Exiting out. Main engine cutoff. CO2 separation. Engine ignition. We have a successful launch. Okay. Rocket is running to Earth. Mission successful. So you can see. You can see that your rocket reached space and returned to Earth on a suborbital flight path. Successful launch on 4 attempts. We tried 4 attempts. The last one was the one that was successful. So congratulations. This is what really happens. You can see SpaceX, they started with a lot of launch failures, but eventually they have perfected the, the mission, the design of the rocket. So they're able now to recover the boosters. So that is the whole aspect of engineering. It requires that one needs to be patient and one needs to be able to go back to the drawing board and think outside the box. Brainstorm and be able to do iterations. Ask yourself, if I do a 3-stage, what is going to be the implications in terms of budget? And what are the advantages? What are the disadvantages of using a 3-stage? Probably you'll be able to lift more weight, but at the expense of the risks, the vehicle can be able to fail because of a stage separation. If you're using a very advanced control system, and then you're using a defective propellant system, probably a liquid kerosene instead of a liquid hydrogen, then your vehicle is going to fail. So I'm going to stop sharing and open the session for Q&A. But yeah, before that, after that, then I'll be able to show you the final simulation for an open rocket. Thank you. So sharing. Okay, any session, I've opened the session for Q&A. Thank you. Exactly. Guys, I'm ready to answer any questions. Can I ask your questions? Okay, let me see. If you make a good rocket, but it's over budget, and make a bad rocket which is in the budget, what should you do? If you make a good rocket, but it's over budget, you cannot be able to make a good rocket that is over budget because you've been allocated a budget. For example, I've given you $10 billion, and you're going to design a vehicle that is more than $10 billion. You'll not be able to put that vehicle into, into development, because then you'll require extra money. So the reason we design a vehicle is that also in space, we do not need to over-design a vehicle. For example, you want to attain interplanetary transfer mission, then or you want to attain a low Earth orbit mission or a suborbital flight. Why will you have 3 stages when you're doing a suborbital flight? That is because you're over-designing the vehicle for a mission that is not supposed to be designed for. So we always design a vehicle for a typical mission, and that is why you can see the Starship vehicle is used for deep space interplanetary mission as compared to a Falcon Heavy or a Falcon 9, which is used just for low Earth orbital missions or geostationary transfer orbit missions. So I don't think you can be able to, yes, you can be able to make a good rocket, which is over budget, but you'll not to be able to put that rocket design into production. So that is the the downside of making a good rocket, which is over budget. Yeah. I'm open to questions. According to the program, if the risk is high and the cost is low, will the rocket still crash? Well, it depends with the way you've designed your vehicle. If you design with the risk very high, but you've put countermeasures, for example, you've put redundancy. For example, instead of just having only one form of control mechanism, you have two forms of control mechanism. Then you can't be able to launch the vehicle and it will still not crash. But then you need to be able to test the vehicle system by system before you can be able to really actually launch the vehicle. Yeah. Okay, I can see the last questions. What are the prospects for lighter material like composites for structural engineering in rockets? Well, they are currently being used to be able to replace titanium and aluminum, because even in aircrafts, you can be able to see the current aircrafts, they use advanced composite materials to be able to replace aluminum, titanium, because they're quite expensive as compared to carbon reinforced composites. So basically, composites are also used in forming the tanks for the rocket engine. So the prospects are high in terms of the future, because a lighter material means that your vehicle will be able to carry more payload, because 5% of the rocket weight is basically structural and payload, and 95% is basically fuel. And that's why there are other aspects that come into play when you are launching your rocket. For example, where are you launching your rocket? Are you launching it from a polar spaceport or an equatorial spaceport? Launching at the equator gives an added advantage for extra, so it makes your material more light. Using a lighter vehicle, you can be able to carry more weight into orbit as compared to using a heavy vehicle. So I hand over to Joanne Tanin, and thank you for joining.
Okay, thank you, Stoa. That was an interesting session of learning about rocket design. I hope you got something that you can tell your friends, and we hope to see you next time with maybe your schoolmates, your colleagues, your friends, your neighbors. You're welcome. If you have got any question, maybe you can direct it to Space Club. That's the email of Space Club. Okay, the email is being dropped in the chats if you have any other question. spaceclub@ksa.go.ke. So once again, thank you for finding time to be part of us and to learn about rocket design. I hope we'll see more aerospace engineers in our country as time goes by. Anyway, we have our next webinar end of this month on 27th of July, where we talk about another interesting topic on space weather. We hope to see you. Otherwise, until next time, goodbye.
I forgot, for those who are interested in doing their own rocket design, you can use this software. It's called OpenRocket. It's just a quick, this one, you can be able to download this software. It's called an OpenRocket. And with this one, you can be able to design your rocket. You can be able to design your rocket, and you can be able to do simulations. You can be able to launch it the way you want. You can be able to modify the nose cone shape from what you really want. So it's called OpenRocket. You can be able to get it online. It's free, and then you can be able to do your flight simulations. You can be able to do everything you want with this software. Yeah, it's called OpenRocket. You can find it online. Then you can be able to design and test your rocket before you are able to really put it into consideration. Thank you.
See you.